Hello everyone. Now I want to talk about a surface representation that's completely different from polygon meshes and is actually a continuous representation. So we're not going to have to sample vertices and glue things together. We actually will have a full representation of the surface. So one example of something like that you saw before was the sphere, right? We defined the sphere as a locus of points that satisfied some equation. So we'll be doing a similar thing here in just a more general setting. Now, we're going to do surfaces tomorrow, but I'm going to start off by talking about curves because they're simpler. So I'm going to talk about something called a Heightmap today, and tomorrow we'll talk about a volumetric map. So before I dive headfirst into the math, let me show you a couple pictures. Okay, so this should look fairly familiar. This is our good old Gaussian Blob. So we drew this with a shader before, but what it is a blurry circle. So it's just that equation, e to the negative x minus center x squared plus y minus center y squared over some radius squared. And what that does is it gives a gradual fall off away from the center. So we can change the center, right? I can move this to the left. I can move it back. I can change the radius, maybe make the radius a little bit bigger. Like that, okay. But at the end of the day, what this really is a 2D function over this square domain here. So the domain has an x from -1 to +1 and a y from -1 to +1. So I'm keeping the coordinate system that we're used to in OpenGL. So it's a function of two variables. As you see by its definition up here, it takes an x and a y. And the way it's plotted here is that the brightest values are the largest values of the function. In this case, it's e to the negative something. So the largest value can be is 1, and the smallest value can be is 0. So at the center of the circle, it's a 1, that's the brightest. As it fall away, in the limit, it goes towards 0 as I go far away from the center. Okay, so this is mostly a review, but I wanted to just remind you that this is a function. One way to think about an image is as a function of two variables. Now here's the really trippy thing. So here's another drawing of this. Not exactly the same as this one up here, but you can see a similar pattern. But watch this. All right, look at that. That is crazy. So what did I do here? Somehow I turned this into a 3D drawing. Well, I kept the x and the y coordinates as they are, based on this square up here, but then I actually used the function value as my z coordinate. So very cool. I can actually make a 3D shape like this. Now there are some limitations of the kind of shapes that I can make. This can't have a cave in it, for example. But there's a lot I can do. So let me show you. I can make, for example, I can make a couple of mountains if I add a Gaussian to a Gaussian. So if I make a function which is a Gaussian plus another one of these Gaussians, I'll move this one maybe to the left a little bit, and I'll move this one to the right. Okay, so now I see two mountains actually, and they overlap there. I guess I'll move them a little bit further so they don't overlap quite as much. Okay. I can also make one of them a valley if I subtract like this. So now it's a valley. It's pretty cool. I can also make the other one a mountain, but make it shorter. So I'll say 0.5 times the Gaussian there. And there you see that. So this is what people do to make terrains. They use Heightmaps in graphics because it's much easier to set up a Heightmap than it is to define a surface from scratch. And you can just draw them like this and then there they are. So that's a pretty neat way to design and represent surfaces. Now, there's another thing I can talk about with Heightmaps called Levelsets. So if I consider, for example, all of the points in x and y, so all of the xy coordinate pairs that satisfy that this function equals 0.27 is what I have there, roughly, then they're drawn here as these loops. And you can see I drew them down here with that height. So here as I'm moving up towards a height of 1, here I'm moving down towards a height of 0. And I'm drawing all of the points. Really, I want to focus here because here are the curves that I'm talking about. These are level set curves that I'm designing. So these loops here. This is what I get when I consider all the x, y's that satisfy that the function is supposed to be a particular height. All right. So now that you've seen the picture of what height maps are and what level sets are, let me just throw down a little bit of math. So a level set you can define is just so we'll say, yeah, so level set of a height map f of xy at height z is set of all points xy, so that f of xy equals z. It's very straightforward. I just put into some notation what I already told you. A level set is all the points that I can find that satisfy this equation, that my function is equal to a particular height. So here is height 0.6, so I only had points on this mountain here. We'll go down to height 0.3, then I also have points on this mountain around there. Okay. Okay, now another thing you can show is something that, those of you who haven't had Calc 3, the language might be a little strange, but just bear with me. So the normal at a point xy satisfying this relation can be computed as the partial derivative of the function. So the x coordinate of the normal is the partial derivative of this function with respect to x, and the y coordinate is the partial derivative with respect to y. Now before I dive in, or before I drive myself crazy trying to explain that, let me just give an example. And I definitely typed these equations out ahead of time because they are nasty. So here is the same thing that I wrote in code a moment ago. So what this in code now is in an equation. So if you can write the code, you can write the equation, okay? Don't be too afraid of that. You've been writing functions since 173. It's just a little nasty to write down all in one place. So okay, so here it is. So I want to find all the z's, so I'm trying to find a level set, all the x and y's that satisfy this equation. So a particular height. All right, how the heck do I solve this? I want to solve the x and y's that satisfy this. Well, one thing I can do is, I don't really like the e there. Let me get rid of that. So what I can do is take the inverse function of both sides. So take the natural log of both sides. That brings what was in the e down. So now I have natural log of z is equal to negative this thing. Okay, now if I multiply both sides of this equation by negative r squared, then I end up with this, which is the equation for a circle, if you look at it. So you remember from your SAT, x minus center x squared plus y minus center y squared is equal to negative, well, in general, it's equal to the radius squared. In this equation, we find that the radius squared of the level set is negative r squared, whatever that was here, times natural log of z. Now this is actually a positive number because remember I told you the largest that z can be is 1 for these Gaussians. So 1 natural log is 0, so that's just the point up there. You have to be exactly at the center to satisfy that. So if I go up to 1, you see hardly anything. Really just a point. Okay. Anything less than 1, natural log is negative, so you see this whole thing is positive. But what's really interesting here is that you see mathematically that the level sets of this Gaussian are circles, perfect circles. That is the equation for a circle. Okay, very cool. Now what about the normal? Well, here's where we do some math. And for those of you who haven't had Calc 3, it's just, so I want to do a partial derivative of this original equation with respect to x. What that means is I'm pretending that y is a constant for a second. And if I do that, I just have to use the chain rule and properties of exponential derivatives. It's actually not that hard once you see what's going on compared to some other derivatives. So that'd be negative 2 times the quantity x minus center x times the original function. If I do the same thing with respect to y, I get negative 2 times y minus center y. Okay, so what I found is the x component of my normal is this, the y component of my normal is this. Now this is kind of nasty, right? The magnitude of this vector turns out to be actually the what's the quickest amount that I can move upwards along this function at a unit speed. But I don't care about that right now. I just want to know the direction. That's what I'm trying to get with the normal. So what I can do, I don't change the direction if I divide the components by a positive or a non-negative number. I guess we should say positive. So if I divide both of these by 2 times this thing, this is the same here as here, so I can divide by that, and I end up with just negative x minus cx y minus negative y minus cy. So this is a vector which is in the direction of the normal. Let me simplify that a little bit by distributing the negative. What I find is that I'm saying that the normal is center x minus x, center y minus y. So let me quickly draw this out. So as we established, the normals, the level sets are perfect circles. So if I pick a point on the level set that actually satisfies the level set condition, we'll say it's xy. And this is a circle that's going to be centered at cx, cy, as we showed. Then what this equation is saying is the normal vector is a vector that goes from the point xy to the center. So cx minus x, cy minus y. That is this vector. Now what's interesting about that is before when I derived the normal for the sphere, I told you it was actually going the other way. Right? So it seems like we got the direction flipped here. But the reason is because when we compute a derivative, we're computing something in the direction of a steepest ascent. So we're looking, what is the direction that brings you towards a higher value of the function the most steeply? And if we look back at this picture, well, if I'm on a level set somewhere, really, in order to move up, I have to go straight. The fastest direction to move up is going straight in, which is a little easier to see if I go on the mountain. If I walk actually parallel to the tangent, then I'm going to stay at the same height, right? That's going to take me around the circle. But if I walk perpendicular to the tangent, that's the quickest direction that I can walk on the way up. So that's what this is telling me. So it gave me a direction that's pointing inwards towards the max. Okay, now if I do a valley, then it'll point the other way. So if I make this negative here, then actually that negative distributes through the derivative as well. And what I'll see is if I happen to be in the valley, then the direction of steepest ascent is actually out this way. Okay, cool. So that's kind of all I want to talk about for the math. The rest is going to be just pictures and algorithms. So this, by the way, this valley, I have a loop around something that's called a local min. So as long as I'm greater than the value at the depth of that valley there, then I have a little loop there. Conversely, if I'm below this peak here, then I have a loop. That's called a local max, that peak. And so what you see is, let me add another one in here. A slightly different location. So let me just put it maybe centered at 0. I'll put it up. Okay. So what you see is actually it's possible to, if I go above the local max of this mountain, then I don't have any components of the level set there anymore. So the components of the level set are created as you go down past a max or up past a min. Okay, so here's some maxes, there's a min there. Now, there's one other interesting kind of point that can happen here. You can think of it like a pinch point. It's also called a saddle point. So let me bring this down a little bit. I'll bring this over a little bit and I will show you what this looks like. Okay. So notice how, okay, let me show you with the level set first. So, okay, so look, if I start at this height of 0.38, these level sets, the level set has two components, two loops. But as I decrease this a little bit, eventually it pinches off. You see that? And turns into one loop. Okay. So the point at which it does that is called a saddle point. And you can see, you know, how it got its name. Let me see if I can really hone in on it there. 0.285 maybe? 0.285? No, it doesn't like that. Okay. But a saddle point is a point where if you go along one direction, it's going down. But if you're going along another direction, it's going up. So you can think, imagine this is a horse that you're sitting on with a saddle. There's your left leg, there's your right leg, there's where you're sitting, and then there's the front of you. So that's called a saddle point. And that's where we get the pinches. So that's basically all I wanted to talk about for this. I just want to do a couple quick questions about what's a saddle, min, and max. But look, see, this is some cool ways of designing surfaces, and this is a continuous representation. So I can sample this anywhere inside this domain, and I'll get a value. Okay.